So this is the next lecture, and this is I will wrap up. I was planning to have a break in this series. Also, I will try to upload the AC theory and about the AC theorems for network theorems for AC circuits. But this is one of the important theorems for DC circuit is Norton's theorem or the Thevenins theorem. So whatever we have learned so far was about the active and the passive elements. Like the active elements were the ones which is having the current or the energy sources in the circuit. Then we saw about the KCL, then we saw about the KVL, then we saw about the mesh analysis and loop analysis. Also we saw about the superposition theorem and the nodal method for solution uh, of like again so it's also possible sometimes to solve large networks using theorems like Thevenin's theorem and Norton's theorem. So these kind of solutions theorems are mostly useful when you want to find out the load current. So in large networks, like there could be the network could be a power system. So the power system could have a generator and it could have the transmission line, etc. So the network could be a transmission line, etc., and there could be a load which could be like the something like a factory which could be supplying, which the network is supplying. So it could be necessary to find the load current, and when you are having a large network, it could be very much to find the load current, etc. Just taking an example for the application, it could be easy to find by finding the equivalent voltage of the circuit and by having a equivalent resistance of this network. So why the RTH is a resistance, equivalent resistance of this network, and the V is the equivalent voltage of this network, while the current will be I Thevenin which will be flowing, or I load which will be flowing. And looking into this circuit, you have removed something. So what you have removed is that you have removed the load resistance. So once you connect the load resistance back, you will be able to easily find out the current flowing through the load resistance. Also, the formation of solving the circuit in this way is known as the Thevenin's network or the Thevenin solution, by finding the Thevenin's equivalent resistance and finding the Thevenin's voltage. So that was the Thevenin's circuit. Again, it's possible to, once you have found out the Thevenin's network, it is possible to replace the voltage source by a current source, and you can do that by VTH upon RTH. This will give up something like ISC or I Norton, which will be the which is replacing the Thevenin's voltage source by a current source, and you can now put the equivalent resistance and the uh, load resistance in parallel. So you will now have equivalent resistance or the Thevenin's net resistance in parallel to the current source. So you have found out the current or the I by using VTH divided by RTH. Then you have put the RTH in parallel to the current source, and now here you will have the load resistance RL. So to find out the load current, we will have to solve this uh, equation, or to you will have to consider this in parallel. But this is how the Thevenin's Norton's network can be represented. Next, the different steps to solve the Thevenin circuit. So while you are trying to solve the Thevenin circuit, the first step would be to uh, connect to make the load resistance open. So if you want to find out the current through the load resistance, that is RL, then you will have to make this load resistance open, and then you will have to find out the voltage, that is a V Thevenin or the equivalent voltage or the open circuit voltage across this open, and then you will make all the voltage sources open and make the current sources short, and after that you will find out the equivalent resistance, that was RTH. So this RTH could be found out after that, and this RTH would be coming in series with the voltage or the VTH, and then there will be the load resistance. So that was what I explained, and The steps to find out the Norton's equivalent circuit should be to make all voltage sources open and make all current sources short and find the equivalent resistance RTH. And once the equivalent resistance is find out, the uh, TH or the I short circuit can be found out. So before you are finding out the Nortons of a circuit, you will have to find out the Thevenins of the circuit. So once you are finding out the Thevenins of the circuit, then you can easily, by using the VTH divided by RTH, that is VTH divided by RTH, you can easily convert that into ISC or the I short circuit or the Norton, and then you can formulate the circuit in the Norton's circuit way. So again, not complicating things, simply taking an example to illustrate the possible solution of a circuit using the Thevenins method and the Norton's method. So suppose this is a load resistance across which you want to find out the load current. So now to find out the uh, load current, you can use the Thevenins method. So you will open circuit this, and now you will have to first find out the V Thevenins across this open circuit. So you will further simplify the circuit. You are applying the KVL to the circuit. So this is a closed path now, so current will not flow through here, so it will flow through here. So there is only one path, so you are applying the KVL to this path, and again you have the I as V naught divided by 10k. So that's the equation for the I which you have. So at this node, so you are substituting that into this equation, and then you are getting the value of V. So you have found out V naught now. So after substituting the value of I, you have found out V naught, which was the resistance across the R1. So you did not know this resistance, this is a voltage drop, and this was a dependent source. So in the first lecture we talked about dependent source. The value of this voltage source is depended on the value of the voltage through this passive element. So this could be a amplifier, this could be op amp, this could be any other element which is directly something related to this. Uh, so you can find out this voltage now, as it is 4 V naught. You have found out V naught, and coming to the next, as you have found out V naught, you can find out, you have already have V1, so you will find out V2 as from the nodal method as V2 is equal to V1 minus V naught. So you found out this, then you have the V3 which is 100 volt, and the V Thevenin is equal to the V voltage across the open, as it was in this diagram. The voltage across the open is equal to the voltage across the node 2. So you have found out the voltage across the node 2, that is V2. V2 is what you have found out. So V2 minus, so V2 is what you have found out, and just a second. So you have got the Thevenin's voltage, equivalent voltage, and then you have found out the RTH by solving the circuit. So what you have done is that you have shorted out all the voltage sources. So after shorting out all the voltage sources, if you go back to the circuit, if you short out this, and if you short out this, in this, if you short out this and if you short out this, already this is open. uh, so what you will have this, you will have this, both this in series now. So you will find out the R equivalent. So you found out the R equivalent as 30 kilo ohm. So that's what you have found out. So again you have the VTH and you have the RTH. So that can be written as, and this you have found out as the Thevenins equivalent circuit, and you have the load resistance. Now you can easily find out the load current if possible. Now again, to convert this equation to the Norton's equivalent, you will have to find out the I short circuit or the I Norton's as VTH divided by RTH, and that's what you will find out. And after that you will get the current as I short circuit as close to 40 ampere, and you can write the RTH in parallel now, and the load resistance will come again in parallel, so you can solve both of that. So in that way you have found out uh, both the Norton's Thevenins equivalent circuit and the Norton circuit in this case. Again, just quickly recapping what was done is that you had the voltage source, you have two active voltage sources, then you have the voltage across the 10 kilo ohm resistance, which is written as V0, and this voltage is dependent on this, and this is your load resistance, so you are open circuiting this. So again, you are having your current I1 through your circuit, or current I through your circuit, which will be the current flowing through the V0 resistance. Also it will be the same current flowing through the 20 ohm resistance. So in that case you are using this to find out the current as V0, the voltage across this which you have, divided by the resistance. So that will give you the current, as it will be the current which will be flowing through this resistance also. So, and using the KVL which you applied to the full loop, and using this, what you found out was, you found out the value of V0, and once finding out the value of V0, you found out the value of the node voltage, this node, and this node is already 140, and you found out the value of this node, also, and based on the value of all the three nodes, you have found out the value of V2. So as you have found out the value of V2, you found out VTH, and then by shorting this you found out the R equivalent. So that was how you solve the full circuit. So it's again, circuits could be more complex and more complex in real exams and other real life scenarios, and for solution. So if I get some time, if I get some new problems, I will solve some other kind of problems also, and based on the response of these videos. And if you want me to solve any specific kind of video, the specific kind of problems, then you can always put that in the comment.